Okay, the recording has started. So we have been going through a lot of the language sections here, and today we want to finish up with the sets and hash tables, and then I want to move on to some dream web development, right? So with that, let's get started with the sets section here. So set provides the functor set.make. We've already seen the functor in an earlier session. You must start by passing set.make a module. It specifies the element type for your set, and you get another module with those element set operations. Okay. So this tutorial goes and mentions about using OCaml 5.1. So I am on 5.1.1, so I think that should be fine. And if you're using an earlier version of OCaml 5, I would recommend you upgrade to 5.1. But if you're using an older version, you need to use elements instead of toList. toList is a new function in OCaml 5.1, or better upgrade to OCaml 5.1. So if we want to work with string sets, we must call set.make of string. This returns a new module. So let's try that in new top. So module string set.make of string. So after naming the newly created module string set, OCaml's top level displays the module signature and all the functions are returned. This module also defines two types: element, which is string, and then we have a type T, which is set.make of string.t for the sets. Let's look at how to create a set. We can create an empty set using string set.empty. So let's do string set.empty. So here OCaml top level displays a placeholder abstr instead of the actual value, right? However, converting the string set to a list can be done with toList, as shown in the example here. So I can say string set.empty string set.toList. Okay, so we get a empty list. Now a set with a single element can be created using string set.singleton. Okay, so let's try that example here. String set.singleton hello, and we can do the toList for it as well. Hello toList. Okay, so we have the string list with the singleton string hello. We can convert a list into a set using string set.off_list. Let's try that. So we have string set.offList hello, hi. Also do string set.offList hello, hi, toList. So we have the string list hello and hi. There's another relevant function, string set of sequence. that creates a set from a sequence. Now let's look at working with sets. So let's look at a few functions for working with the following two sets. First one is first set, and then we have second set. So we do string set of list, okay. Then we define second set, string set again of list. Right. Now we can add an element to the set using add here. Let's try this. So I can do string set dot first set add good morning to list in lowercase. Okay, so we've added good morning to the list. So the function string set dot add with type string, the string set returns a string set, right? It returns a new string set. That is very important. Sets created with the set dot make functor in OCaml are immutable. So every time you add or remove an element from a set, a new set is created. The old value is unchanged. So let's look at removing an element from a list. We can do string set in first set. We remove hello to list. Okay. So the string set dot remove method takes a string and a string set. It returns a new string set without the given string. So it's immutable. We can also do union of two sets. So I can say string set dot union of first set, second set to list. Okay, so all the elements in both the first and second set are listed here. You can also do intersection of two sets, that is string set use the inter function with first set, second set pipetted to list. So only hi is common. We can also subtract a set from another. So let's do with the diff option, first set, second set to list. So here we remove the elements of the second set from the first set. We can also filter a set. So let's try this example here. We have good morning, hello, hi, call string set dot of list. We call filter string dot length str less than or equal to 5, right? And then string set dot to list. So we want to filter all the strings whose length is less than or equal to 5. It's only these two strings. Again, it creates a new set by keeping the elements that satisfy the predicate function from the existing set. Now we can also check if a element is contained in a set. So let's do good morning, hello, hi, string set dot of list. string set dot member of hello. Okay. To check if an element is contained in a set, we use the mem function. Now, the set.make functor expects a module with two definitions, a type T that represents the element type and a function compare whose signature is T to integer. The string module matches that structure, so we can directly pass string as an argument to set.make. Of course, there are other modules that have this structure including int and float, so they too can be passed to set.make to construct a new module. Now, the string.set module we created uses the built-in compare function provided by the string module. So, if you have not already gone through the functors section, I would encourage you to watch that video again. Now, for example, if you want to create a set of strings that perform a case insensitive comparison instead of the case sensitive comparison given by string.compare. So, we can accomplish this by creating a new module using set.make. So, let us create this. We say module CISS, which stands for case insensitive string set, set.make struct type T is string, let compare AB is compare string dot lowercase ASCII A, and then we have string dot lowercase ASCII B, and called end, right. So, this is the new resulting module CISS, and let us try the module here. We do CSS dot singleton hello, CSS dot add hello, CSS dot toList. Okay. So, we see here the value hello is not added to the set because it is considered to be equal to the lowercase hello. It's a case insensitive match. We can also use any type for elements as long as we use the meaningful compare operation. Let us see the definition here for RGB, red or green, blue. We have module SC is set dot make struct. We have type T is color, right, and then we have the compare function. Compare AB is, we do match AB with this red and red, return 0. This red and green, return 1. Red and blue, return 1. Green and red, return -1. This green and green, we return 0. Green and blue, return 1. Blue and red, return -1. Blue and green, -1. Blue and blue, return 0, and we call end. Good. So, this is an overview of OCaml set module, which we created using string set module using the set.make functor. We also looked at how to create sets based on custom comparison function. So, I would encourage you to go through the set documentation in the standard library. So this concludes the set part. Let's look at hash tables. Let me paste that link in the chat as well. Learn language sets and hash tables. Okay, the URL for sets is plural. Let's quickly go through this. So hash table implements an efficient mutable lookup table, right? To create a hash table, we should write and use hash table dot create 1 2 3 4 5 6. So 1 2 3 4 5 6 is the initial size of the hash table. So this is a best guess as to the amount of data that you will be putting in the hash table. The hash table can grow if you underestimate the size. Okay, so let's look at the type of my hash. Okay, so we have these week 1 and week 2 refers to the key and value types. Now there are no concrete types filled in these slots because the type of key and value are not yet determined. Okay, the underscore indicates the key and data types. Once chosen, they will be fixed. Okay. So you can't use a given hash table with ints for keys and then later use a string as a key in the same hash table. That doesn't work. Let's look at some functions to operate on my hash. So important thing to remember is in a hash table the modifications and updates are in place. So unlike a map, another hash table is not created, everything is changed in the same table. So you would use something like let my hash. So let's try adding to our my hash. So we say hash table dot add to my hash hello hash table dot add my hash hi, and say hash table dot add my hash hug. Now I'm giving the same key h, but I'm giving different value here, right? Now I'm doing hash table dot add my hash h hard. We can do hash table dot add my hash wimp, hash table dot add my hash world, and finally hash table dot add my hash wine. Okay. Now if you want to find one element in my hash that has a h in it, we can do hash table dot find. Okay. Now it returned just one element. The element was the last one that was entered in h, which was this entry here, right? Now suppose if you want to find all the elements that start with h, so use the find all method. So you can do hash table dot find all my hash h. Okay. Returns all the strings that start with h. if you remove a key, its previous value becomes again the default one associated to the key. So if I remove my hash table dot remove my hash, okay, and if I again go and ask for returns hug. So the keys represent variables that can be temporarily masked by local variables of the same name, right? So we had hard, hug, hi, hello. Hard is gone, so the first one is hug. Okay. We can verify this by doing find all. It is the first that was returned. Sometimes you might want to replace the previous entries, so you can use hash table dot replace. So let's try this example. We have hash table dot replace my hash t try. We do hash table dot replace my hash test. Find all my hash t. Okay. Now we can do hash table dot remove my hash t and hash table dot find my hash t. So now this throws an exception because it's not found, right? If you want to check if there is an entry in my hash, you can use the member function. So I can do like hash table dot mem my hash of h, just there. It's a very quick introduction to the hash tables. I would again encourage you to go through the standard library and go through the methods and other functions provided by hash table and try it out in UTOP. Make sure that you're using OCaml 5.1 at least for trying out both sets and hash tables. This concludes this session. In the next stream, we will look at doing some Dream web framework development now that we have gone through a lot of the OCaml syntax and semantics. I will make the video available on the YouTube channel, and let me also push the code snippets from today's session to the GitHub repo, so you can quickly refer and try this out on YouTube. Okay. Right. With that, let's stop here.